Minor loop feedback is a classical method used to design stable, robust linear feedback control systems using feedback loops around subsystems within the overall feedback loop. The method is sometimes called minor loop synthesis in college textbooks, some government documents. The method is suitable for design by graphical methods and was used before digital computers became available. In World War II, this method was used to design gun-laying control systems. It is still used now, but not always referred to by name. It is often discussed within the context of Bode-plot methods. Minor loop feedback can be used to stabilize op-amps. Example: telescope position servo. This example is slightly simplified from the control system for the Harlan J. Smith telescope at the McDonald Observatory. In the figure there are three feedback loops: current control loop, velocity control loop and position control loop. The last is the main loop. The other two are minor loops. The forward path, considering only the forward path without the minor loop feedback, has three unavoidable phase shifting stages. The motor inductance and winding resistance form a low-pass filter with a bandwidth around 200 Hz. Acceleration to velocity is an integrator and velocity to position is an integrator. This would have a total phase shift of 180 to 270 degrees. Simply connecting position feedback would almost always result in unstable behavior. Current control loop. The innermost loop regulates the current in the torque motor. This type of motor creates torque that is nearly proportional rotor current, even if it is forced to turn backward. Because of the action of the commutator, there are instances when two rotor windings are simultaneously energized. If the motor was driven by a voltage-controlled voltage source, the current would roughly double, as would the torque. By sensing the current with a small sensing resistor and feeding that voltage back to the inverting input of the drive amplifier, the amplifier becomes a voltage-controlled current source. With constant current, when two windings are energized, they share the current and the variation of torque is on the order of 10%. Velocity control loop. The next innermost loop regulates motor speed. The voltage signal from the tachometer is proportional to the angular velocity of the motor. This signal is fed back to the inverting input of the velocity control amplifier. The velocity control system makes the system stiffer when presented with torque variations such as wind, movement about the second axis and torque ripple from the motor. Position control loop. The outermost loop, the main loop, regulates load position. In this example, position feedback of the actual load position is presented by a rotary encoder that produces a binary output code. The actual position is compared to the desired position by a digital subtractor that drives a DAC that drives the position control amplifier. Position control allows the servo to compensate for sag and for slight position ripple caused by gears between the motor and the telescope synthesis. The usual design procedure is to design the innermost subsystem using local feedback to linearize and flatten the gain. Stability is generally assured by Bode-plot methods. Usually, the bandwidth is made as wide as possible. Then the next loop is designed. The bandwidth of this subsystem is set to be a factor of 3 to 5 less than the bandwidth of the enclosed system. This process continues with each loop having less bandwidth than the bandwidth of the enclosed system. As long as the bandwidth of each loop is less than the bandwidth of the enclosed subsystem by a factor of 3 to 5, the phase shift of the enclosed system can be neglected, i.e., the subsystem can be treated as simple flat gain. Since the bandwidth of each subsystem is less than the bandwidth of the system it encloses, it is desirable to make the bandwidth of each subsystem as large as possible so that there is enough bandwidth in the outermost loop. The system is often expressed as a signal flow graph and its overall transfer function can be computed from Mason's gain formula.